Welcome everyone to our solar photovoltaics course. Today we are having a 7th week and our 4th module. We are discussing about the organic nanoparticle solar cell. In the last lecture you have seen that we have discussed about what are the advantage of using organic nanoparticles over the conventional bulk polymeric system, and we have also seen that while the fabrication process that will depends upon what is our end objective or what is our ultimate objective. So, now in today's lecture we will discuss about the different fabrication method or different synthesis method of these organic nanoparticles. Now, these methods for fabrications of the nanoparticles, they can be broadly classified into two different categories. One is bottom up and another is the top down. Now, the bottom up methods, that is also called chemical methods, and the top down method, that is called the physical methods. Now, you see that for the bottom up methods, as the names suggest, again the self assembly is an example of a bottom up method. So, for example, you see that there are a lot of these cylindrical structures are there, right. In this picture there are 5 cylindrical structures are there. Now, what you can do, you can assemble them together to make different kind of geometry. This is a self assembly. Okay. So, you start from a minimum number of the structure or unit structure and you make a larger structure. This is a bottom up technique. For example, self assembly, molecular patterning. Okay. And to make this kind of from one of the unit structure to make this kind of structure or pattern, you need some physical or chemical triggers. For example, changes in pH, concentration, temperature, and then the top down approach. For example, the lithography, where you start with like a big structure and then like by etching and by nanolithography you make like a small structure. So, one from the smaller structural unit you make a bigger structure, like, but still it will be in the nano domain, and in another case starting from a macromolecular structure you come on the other direction and get a nanoparticle system. Now, this physical method, they can be like either by mechanical grinding or by laser ablation. Now, the mechanical grinding is very like simple to understand. Many of you has seen the grinding of the coffee powder. So, once from the coffee bean, so they have been put in some kind of ball machine or grinder, and then they have been grinded according to their size to a very small powder. Now, if you take up this one of the spoon of this small powder and if you look under the microscope, you will see some kind of nanoparticle systems there. In addition to that, there are a lot of big particles are also there, right. So, the grinding method is same thing like that. So, instead of this coffee bean, let us say I take a carbon material, any kind of carbonaceous material, and then I started grinding them in some kind of grinder. So, what will happen finally, like depending upon the force of the grinding and the duration of the grinding, we can control the size or the particle size of this finally whatever we obtain from that engineered carbon nanomaterials. The second method is the laser ablation. So, in the laser ablation what happens, like on the target substrate a pulsed laser beam falls on this. So, now pulsed laser beam, the average intensity of the pulsed laser beam is quite high, somewhat around like gigawatt per centimeter square. Now, if this intense laser beam falls on this substrate, so what will happen, whatever the atoms, molecules or ions that stays on the top surface, so they will like peel off from the top surface or from the target, and they will deposit on your material, or you can get inside the chamber some small particle which have been ablated by the laser from the target substrate. Now, this grinding, they can be classified as a dry grinding or wet grinding. Okay. So, dry grinding, a very commonly used technique is ball mills. So, all this like metallurgical engineering or in material science people use this ball mill grinding for making the smaller particle size, and then there are jet mills are there, and the wet grinding they are diso cubes. Now, ball mill is very like simple geometry. You have this kind of spherical crucible, and you put first your large particles, and then by the mechanical force, so the milling happens, and then by the successive collisions and by the force of the grinding, so it becomes smaller and smaller particle. And in a jet mill, like we use a compressed air, and in the input we use the larger particle, and by fluxing the compressed air and by the rotation of the gel mill, the smaller particle comes through the outlet. Now, what are the drawbacks of the mechanical synthesis? First of all, like whether it is a ball mill or a jet mill, there can be impurities from the mill, and then the destruction of the thermally unstable. So, once you do this thing, some of the particle becomes like some of the particles may be thermally unstable. The presence of a relatively large number of particles, yes. So, the polydispersity is quite high in this system. and limited possibility of a control over the size. So, in the ball milling process we cannot control the size to a very finite or very fine tuning, we cannot do that, and their wide size distribution and also their irregular shape. Since it is kind of like a rough mechanical process, so in addition to the polydispersity, also here we cannot get a very fine tuning over the particle size, and you get a larger particle size and their wide distributions. So, these are some of the disadvantages associated with the mechanical grinding. Now, in laser ablation, that the organic nanoparticles fabrication by laser applications, that dates back to 2000. So, it was quite old method, and we use it by preparation in the suspension and impact of an intense laser beam. As you can see here, like this is the chamber and here is the solution, and we have put a glass coil, right, and then the laser beam is reflected by the mirror, which is a pulse laser beam on the solution, okay, and the fragmentation of the grains and the transparent colloidal solution we finally obtained in the solution method. Preparation of the stable colloidal solutions in the absence of the stabilizers, control the size, wavelength, the laser pulse width and fluence. Increase in the laser radiation fluence results in a decrease in the nanoparticle size, and in a nanosecond region it is a photothermal process, in a femtosecond region is a photomechanical process. So, the ablation, so since this depends or since it is done by using a pulse laser beam, now you know that this pulse laser beam can be a nanosecond Nd:YAG laser beam or can be a Tie-Sapphire femtosecond laser beam. Now, if you use a nanosecond Nd:YAG laser beam, then basically the ablation process is the photothermal process. So, not only the light, but the thermal heating that is providing the energy for fabricating this nanoparticle. But in a femtosecond region where you are using a femtosecond 800 nanometer laser beam, then in addition there are some thermal effect will always be there, but the mechanical photomechanical effect that plays a dominant role for fabricating this nanoparticle system. Now, what are the drawbacks of the laser ablation method? First of all, only a small amount of dispersion is formed. So, since like we focus the laser beam on the solution, okay, so and the beam diameter, depending upon the expansion of the beam or the beam diameter, how many particles will be formed, that will be dependent, right. So, we cannot make a lot or large amount of particles by this method and may cause photochemical decompositions. What will also happen, some of the materials they are like susceptible to the chemical degradation. Now, once you expose to the light, so what will happen, like because of the light induced degradation can also be prevalent. So, this methods is also limited to certain materials. So, you cannot use any materials, we have to make sure that this material is also photostable. Okay, the another types of method is the chemical method. Now, there are several kind of chemical methods are there. For example, solvent replacement. So, basically you dissolve your material in one kind of solvent where it dissolves well, then I can put an anti-solvent which has a huge polarity difference with the parent solvent, and the anti-solvent will gradually replace the parent solvent. Anti-solvent for precipitation, again like let us say I take an arbitrary material A and I dissolve it some kind of organic solvent, let us say dimethyl formaldehyde DMF, and then I take another solvent which does not mix with DMF. Okay. For example, I can take like chlorobenzene or toluene. I know that DMF and chlorobenzene or toluene has a difference, or diethyl ether, they have a huge difference in the dielectric constant, almost around, if you take DMF and diethyl ether, their dielectric constant difference is almost 32. So, they have a huge difference in their polarity. So, what will happen, like they will not try to mix with each other. So, and one solvent is called the anti-solvent of the other. So, what will happen, like once you put the anti-solvent, so the material will try to precipitate. So, one can make a nanoparticle by that approach also. Chemical reduction in solution, that is a like common technique, some kind of chemical reaction or the reduction can happen. Ion association can happen, synthesis of nanoparticle in the water oil immersion. So, now we know that oil and water, they do not mix with each other. If you put a oil drop in the water, so what will happen, like this oil drop will try to minimize their surface energy, right. So, they will make a micellar structures. So, this kind of micellar structures like has also been used for fabricating organic nanoparticles. There are several methods for making this kind of nanoparticle assembly, we will discuss that in later. And then photochemical method, I mean one can also induce the chemical reaction by shining the light, that is called photochemical method. And the use of supercritical fluids. So, if someone like condense or evaporate or allow the fluids to condense beyond its supercritical temperature, so one can also get a supercritical fluids. And then cryochemical synthesis and modification of nanoparticles. And also another advantage of the nanoparticle is that you can surface engineer its side groups. So, that means you can put whatever the optical group, whatever the electrical group you want at the surface of the group, and that actually increase the diversity of the application of the nanoparticle. Okay. So, first is the solvent replacement. Carotene and PVP were dissolved in chloroform, and then chloroform was evaporated in vacuum to form a solvent mixture of beta carotene and PVP. So, basically we have taken carotene, okay, and PVP, this is a solvent, these two has been dissolved in chloroform, and chloroform was allowed to dissolve. So, chloroform has a boiling point of 65 degree centigrade. So, if you leave the chloroform in the ambient atmosphere, so it will slowly evaporate and it will leave the system. So, what will happen it will form a solid mixture of beta carotene and PVP. Upon the addition of the water to the solid mixture, an aquareal colloidal suspension form, which is called the hydrosol. Okay. So, this is a very easy method of replacing a solvent and then make a colloidal dispersion of a nanoparticle. Some benefits of there, this process is very easy, it is a very mild condition you use. For thermally unstable compound, this method is good and relatively simple and accessible. But some of the drawbacks is that low production performance, cannot be used for substance poorly soluble in organic solvent. Let us say beta carotene is soluble in chloroform, but if it does not soluble in chloroform, then you cannot use that to make a dispersion or make a colloidal dispersion using the chloroform, and very dilute solutions are obtained. Now, one of the very important technique which have been used for fabricating organic solar cell devices is the mini emulsion technique. So, it is an idealized mini emulsion technique. It is an idealized concept in heterophase polymerization to generate small, homogeneous and stable droplets of monomer or polymer precursors, which are then transferred by the polymer reactions to the finer polymer latex, keeping their particular identity without serious exchange kinetics being involved. So, this is the same concept like an oil in water emulsion. So, I gave an example, like if I put an oil drop in water, what will happen? They will form a micelle. So, similarly, let us say I take a polymer which is soluble in some kind of organic solvent, let us say chloroform, okay, and then if I put this chloroform which contains the polymer in the water, so what will happen? The chloroform and the water will not dissolve with each other, they will not try to mix with each other. So, they will try to minimize the surface energy. How they can get a surface energy? By getting minimum surface energy, by getting a spherical geometry, right. So, inside this spherical geometry, the polymer chain, they will coiled up. So, basically I will have a spherical geometry where the polymer chains has been coiled up inside the spherical geometry, but this system is not very stable. So, it is a dynamic system, right. So, now in the water, if I put some kind of surfactant which is an ambipolar compound, that means it has an hydrophobic group and it is an hydrophilic group. So, then the surfactant molecule can decorate the polymer chains outsiding or decorating from the outside, so that the polymer chains or the chloroform phase stays inside and its hydrophilic ends of the surfactant stays outside in the major solvent. So, this kind of system is a dynamic micelle, like where you can get a nanoparticle of the polymer which have been embedded in a minor phase which have been decorated by a major phase of the water. And the second method is that the reprecipitation technique. So, the reprecipitation technique, here we do not use the surfactant, here we use one solvent which is poorly miscible to the another solvent and we add in an excess amount to make a nanoparticle. Now, today we will discuss about the mini emulsion techniques. It is a very simple technique, even you can do it in your undergraduate lab without requiring for a very sophisticated instrument. Now, this cartoon which I am going to show you now, that will explain how simply one can make a organic nanoparticle in a dispersion. You first take any kind of organic material, let us say you take a polymer, okay, P3H3, and you dissolve it in some kind of organic solvent. So, the red color is showing a P3H3 polymer which is dissolved in a organic solvent. Then what you do, you gradually add this polymer solution droplet which is in chloroform to a water solutions, and this water contains surfactant. So, what will happen now? So, I have a chloroform phase and I have a water phase. So, I have a basically an oil phase, I have a water phase. Oil and water, they will not mix with each other. So, this oil phase, they contains the polymer chain. Once you put this oil phase in this water phase, so basically they will make a colloidal dispersion. And how to get how to get rid of this the size effect here? So, once you put this chloroform inside this aqueous system, so they will try to minimize their surface area by getting a spherical volume. Now, if I put an external mechanical force by some form of steering, either it by a bath sonegation or by probe sonegation, so I can make different size distribution of the particle, and that is done here. So, basically what we do here, we steer this dispersion by some kind of mechanical force, and that mechanical force is provided by sonegation. Either you can use a bath sonegation or you can use a probe sonegation. So, what will happen, like this chloroform in the water, they will form a chloroform dispersion, and this dispersion contains the polymer chain. Now, if I heat this dispersion beyond the boiling temperature of the chloroform, so whatever will happen, the trapped chloroform will detrap from the solution. So, basically like you have this let us consider this spherical things where the polymer chains have been embedded now in this chloroform phase, and now I have this surfactant which is decorated from the outside, which stays in a water systems, right. This is your water system, this is your water system, and this surfactant provides the stability. So, this is the chloroform phase and this is the water phase. You can call it this as a major phase, this is a minor phase, okay. And this polymer chain has been decorated by this surfactant molecule. Now, if I heat this chloroform or if I heat this dispersion beyond the boiling temperature of the chloroform, but less than the boiling temperature of the water, so what will happen? The chloroform will slowly leave the system, leaving the polymer chain in the aqueous water system which have been decorated in a micellar structure by the surfactant. So, I have a very constant volume or geometry which contains this nanoparticle or the polymer chain which have been decorated by the surfactant, and all things remain stays in the water, or I basically get an aqueous dispersion of the organic polymeric nanoparticles. Once you heat this solvent beyond the boiling temperature of the chloroform, you can clearly see a color change. So, the color of the polymer will change to a deep brown color like nanoparticle dispersion, and this method is called the mini emulsion technique. So, this is a very popularly used techniques which have been used for making solar cell, light emitting diode, and especially for the drug delivery. Now, since I said that this method is very versatile, that means one can take any polymer and make nanoparticle out of it. So, so basically even we can take a biocompatible polymer and we can take a drug molecule and we can encapsulate the drug inside this core, and at the same time we can encapsulate some kind of imaging probe inside the core along with the polymer and decorate with a surfactant molecule. So, then this nanoparticular assembly, they will contain the drug molecule as well as the fluorescent probe. So, this have been used as a nanomedicine. So, in the case of the nanomedicine or the drug delivery system, this method had also been used very extensively. Now, once we use this method, like you can imagine that previously I have a big polymer chain like that. Now, this polymer chain has been concentrated in a small volume. So, before that it was like this, and now they have been confined in a small volume. So, what is the consequence? Since they are now very close to each other, the electronic interaction or the electronic talking between each of them has been now increased, because now they are very close to each other. So, there is a possibility of the overlap of the electron cloud. So, that we call the enhanced electronic interaction, and because of that you will see a change in their optical properties. So, if we measure the absorptions and the photoluminescence of this nanoparticle, and if we compare with the polymeric system, we see a distinct change, and you can imagine that. So, if we do the absorption spectrum or the fluorescence spectrum of this nanoparticle system, we will see a red shifting in the absorption and the emission spectrum, because this system now acts like an aggregated system, or this system acts like a thin film analog of a same polymeric bulk system. So, the synthesis of the nanoparticle in the water oil emulsion or the mini emulsion technique, it is a very commonly used technique where the preparation of the oil in water emulsion has been used by steering, and that steering is either can be a bath sonegation or by probe sonegation. Transfer of nanoparticles into the water phase, for example by sonegation or high pressure homogenizations. You look at this figure here, the same thing, formation of the water oil emulsion. We have a hot water here and then the hot organic solvent. So, they have made a two distinct phase, oil phase and the water phase. Now if you cool this thing, what will happen? So there will be a nucleation. So oil phase and water phase, they now stays with each other. Now if you cool this thing, there will be a nucleation, and if we can control the cooling, then we can also control the crystal growth. And at room temperature, so basically what will happen, if I apply some kind of pressure, or if I apply some kind of mechanical pressure, so then you can get a smaller and smaller size of this nanoparticle. And finally if we heat it beyond the boiling temperature of this organic solvent, so the surrounding organic solvent thing that will go out, and whole this thing will come, or whole this thing will come in the water. Okay, that is the emulsion polymerizations or mini emulsion polymerizations. So what are the properties of this thing? So first of all, like you see the size. So how you can characterize the properties. So first thing, when you make a nanoparticle, first question which comes in our mind, what is the size of this nanoparticle? There are several techniques to characterize the nanoparticle size. One commonly used technique is called dynamic light scattering, or DLS. In a DLS technique, basically it used Einstein's scattering equation. So you know this Brownian motion. So if I put a pollen grain in some suspended water, so what will happen? Pollen grains will do random Brownian motion. Similarly, this nanoparticle assembly in this colloidal dispersion, they are doing random Brownian motion. Now if I shine a laser light on this nanoparticle, so light will be scattered by this nanoparticle, and we can measure the scattering intensity, and from there by using some mathematical equation we can find out the size distribution of this nanoparticle, and that is the principle behind this dynamic light scattering, or DLS. And then there can be like transmission electron microscopy method, which is an imaging method where you allow your light to pass through your nanoparticle system, and in the detector you get an image of the nanoparticle. Then there are scanning electron microscopy method, is another imaging technique which looks for the backscattered electron. And then there can be scanning tunneling microscope, again like if you have a very thin sample and the very thin nanoparticle layers, so you can use scanning tunneling microscope to get a very nice image of the nanoparticle assembly. Then one can get a surface morphology, topography, surface roughness by doing atomic force microscopy. Again here you use a laser beam which scan the sample surface, and whatever the laser light which have been deflected from the top surface, that have been collected by detector, and from there we can find out by doing some analysis what is the topography of this surface. Then there are this FCS method, then there are NTA method, there are several methods to characterize the size distribution of the nanoparticle. Then to look for the chemical bonding, what kind of chemical bonding exists in here. So one can do either an FTIR or one can do an X-ray spectroscopy. Okay. Now to know that aggregation or disaggregation, or to know that whether this is a real dispersion or whether it is a suspension or whether it is a solution, to know that we can again do the dynamic light scattering DLS to measure the polydispersity index. We can do FFF, we can do UV visible spectroscopy, and then some imaging technique like TEM, SEM, STM, AFM as well as NTA. This is another DLS based techniques. To know the fractionizations, that means how many of them has been fractionized to what percentage, we can get ICP or we can get HPACC. To measure the surface charge on this nanoparticle, we can do a electrophoretic mobility, we can measure the zeta potential or the surface charge again by this DLS method. So these are all characterization techniques of the nanoparticle. One needs to know their size, one needs to know their size distribution, one needs to know their aggregation, one needs to know their chemical bonding, one needs to know their surface charge, etc. And these are the experimental techniques one can find out that. Now the detection and characterization, they depends upon the sample preparation like filtration and centrifugation, imaging technique like TEM, SEM, AFM, separation, one can do the separation by HPLC technique, and then finally some characterization like optical characterization, electrical characterization, etc. Now let us look at for some of the optical characterization for a very common example. For example, we have taken a polymer called P3HT. Okay. This is a polymer which have been commonly used for making organic solar cell, right, and this polymer organics, this P3HT has been dissolved in chloroform, okay, and then we have taken an absorption spectrum of this polymer. So you see that y axis is the normalized absorptions, normalized absorbance, and the x axis is your wavelength. So for a polymer you can see this black curve is its absorption spectrum, but when you make a nanoparticle in aqueous dispersion, you get this red color graph as its absorption spectrum. So what is the difference between them two? So there is a peak shifting happens. So the maximum absorptions per polymer happens around this 450 nanometer, but the maximum absorptions happen here around 550 nanometer. So there is a huge peak shift happen, and also you see the nature or the dynamics or the nature of the peak distribution is different in these two cases. Here you see only one peak, but here you see one peak here, there is a shoulder here, and also I mean the way this has been distributed here, it is also different. And very interestingly, if you take this polymer and make a thin film of the polymer and heat that film at 120 degrees Celsius and take an absorption spectrum, that absorption spectrum will matches with this nanoparticle aqueous dispersion. So, I repeat that if I take this polymer in some kind of organic solvent like chloroform, and if you make a thin film of the polymer and if you record the absorption spectrum, that will mimic the absorption spectrum of this nanoparticle. So, what does it mean? That this nanoparticle dispersion absorption spectrum resembles like a thin film absorption spectrum, and that is kind of expected, because once you have a nanoparticle dispersion, although it is in a colloidal suspension, it resembles or mimics a solid state system. Now, everything in a closed vicinity. Now, in a thin film, what will happen, like you actually arrest the random motion of the polymer chain in a solvent. So, that is why the interaction between the polymer chain enhanced there. So, similarly, like once you make a nanoparticle dispersion, so what will happen, now the distance between the two polymeric chain has been enhanced. Because of that, the interaction between the chain has been increased. That is why although a polymeric nanoparticle in a dispersion system, it resembles the same spectrum like a polymer thin film spectrum. And if we take even a small molecule like PCBM, if you take PCBM, which is a small molecule, we observe the similar trend. This is the PCBM small molecule absorption spectrum in chloroform, and the red color curve is the nanoparticle dispersion in the water. So, you see that the peak shifting happened in the case of the nanoparticle things. So, that means this nanoparticle dispersion can be straightforwardly used for fabricating devices, because for making devices you do not make the devices with the solution. Basically what we take a polymer in chloroform, we take PCBM in chloroform, then we mix them together, and from the mixer we make a film, then we heat the film, and then we deposit the electrode on the two different sides to make the devices. But here the dispersion itself mimic the same properties of the film. So, that means if we mix these two dispersion together, and then if we disperse them or if we self assemble them on a ITO substrate, and then if we deposit the electrode, basically we will have a device. And that was the purpose behind doing this organic nanoparticles things in the solar cell. Now, to go one step further to characterize their size, so we said that this nanoparticle size distribution can be calculated or can be determined by dynamic light scattering. So, this is a dynamic light scattering data. So, in the y axis you have the number and the x axis you have the diameter, and you see that from the histogram this particle size is kind of monodisperse, and they are somewhat around 90 nanometer in size, and the same features one can pick up by doing some ACM analysis here. So, as for example, here we are showing some scanning electron microscope, and you can see that this P3H nanoparticle dispersion, although there are some aggregates there, and that is because of the some surfactants is there, and it is possible that some aggregation happens, but many of the times we can see that very isolated, very nice nanoparticle distribution in the ACM image. Then the next step is that we have this nanoparticles, donor nanoparticle and acceptor nanoparticle. We have this P3H nanoparticle, and we have made the PCBM nanoparticle. One is the donor, another is the acceptor, and both of them in the water. Okay. So, now we mix both of them. So, in one of the beaker we have the donor nanoparticle, in another beaker we have a acceptor nanoparticle. So, we mix both of them, and from the mixture we made a film. So, we coat the film from the mixture, and then we allowed the mixture to dry, or we can also heat the mixture little bit like 100 or 120 degrees Celsius. Okay. So, what will happen? So, now we have these spherical nanoparticles inside the dispersion. Now, once we make a thin film out of that, they will self assembly according to their free energy distribution. So, we have picked up that self assembly distribution by doing an AFM image, which you have shown here, and if you see this image you can see two different colors. One is this very dark color, black color, and another is this yellowish color. Okay. So, this dark color, this dark black color, that is the donor phase, that is the donor P3H nanoparticle phase, and this yellowish color, this is the acceptor PCBM nanoparticle phase. So, you remember that in the previous time when you talk about P3H nanoparticle and PCBM, when you talk about the polymer P3H and acceptor PCBM, we said that we need a phase separated bicontinuous percolated network, and we have seen in one of the diagram that there is a donor phase, acceptor phase, donor phase, acceptor phase. So, that is a bicontinuous percolated network and phase separated. So, phase separated bicontinuous percolated network, and we exactly observe the same thing here in nanoparticle assembly. You see there is a donor phase, acceptor phase, donor phase, acceptor phase. Okay. So, the tapping mode AFM image of an unannealed P3ST PCBM nanoparticle films also show the same kind of topography as a bulk system. So, that means this kind of system provides a phase separated bicontinuous percolated network, that means it can be used for making devices. Let us proceed to make some devices, and that is what we have done. So, what we have done, like we have self assembled this P3ST and the PCBM nanoparticle in one monolayer, and the one monolayer device shows an efficiency of 6% at the peak absorption wavelengths. This graph is called the internal photocurrent conversion efficiency. This is the number of electron generated per incident absorbed photon. So, y axis is my IPC percentage and x axis is my wavelength. So, you can see this IPC spectrum, or what is the number of electrons has been generated per incident photon. From there we can find out that the peak absorption wavelength, the efficiency is 6%. So, that is a tremendous improvement over the bulk system. This is for a one monolayer. So, that means if we make a multi-stack or multi-layer, so there is a room for efficiency enhancement, or we can make an efficiency more than 8% by suitably optimizing this thing and by suitably changing some of the protocol. Well, there are a lot of disadvantages, or there are a lot of things has to be optimized. For example, like we are using here surfactant, right. So, surfactant is like an insulator, and we try our best to remove the surfactant as much as possible. We use like molecular cutoff filter. So, the purpose of using molecular weight cutoff filter is that to eliminate certain molecular weight and to allow certain molecular weight to stay in the system. So, let us say for example, if the surfactant has a molecular weight of 20,000 kilodalton. So, if I use like a molecular weight cutoff filter which cuts up 20 kilodalton and beyond that, so that means only, so it will remove the surfactant from the dispersion and allows the polymer or the small molecule, provided they have a molecular weight lesser than that, inside the system. So, we can choose the molecular weight cutoff filter, and we can do the centrifugation again and again and washing, so that we can make sure that whatever the loosely bound surfactant removes from the system, but still there will be some surfactant in the system, and that acts like a trap state or as like a defect state. So, that is one of the disadvantages in this process. Now, just like a bulk structure assembly, here the nanostructure assembly can also be generated in two different ways. So, you remember when we talked about the organic solar cell, we said that if this is a donor system and this is the acceptor system, we can assemble them by layer, or in a single layer we can mix donor and acceptor, and we can mix them and mix a combined thin film out of that. We can do the similar thing here also. We can take a donor nanoparticle, we can take an acceptor nanoparticle, and we can make a layer by layer film, or we can mix them together, and from mixer we can make a mixer film in that. So, that is have been done here. We started here from the P3ST polymer, and we made a nanoparticle of the P3ST, and we started with another small molecule called NDI, naphthalene diimide. From there we made a nanoparticle, NDI nanoparticle. So, this is your donor nanoparticle, this is your acceptor nanoparticle. Now, both this donor and acceptor nanoparticle, they are physically mixed with each other to make this kind of assembly. Now, one thing has been done here. When we make the donor nanoparticle, we use a negatively charged surfactant. So, that means the surface charge of this donor nanoparticle is negative, and when we make this acceptor nanoparticle, we make positively charged surfactant. So, that means the surface charge of this nanoparticle is positive. Okay. So, this is negatively charged, this is positively charged. Now, what will happen if we mix them together? They will electrostatically bind with each other, and that is what has been shown here. So, if you take a magnified view of this assembly, you see that this donor assembly and the acceptor assembly, they are bound by electrostatic attractions, okay, and we call them as an interdyad nanoparticles. On the other hand, what we can do, we can mix the polymer and the small molecule in the same time together in an organic solvent, and from the mixture we can make a nanoparticle. So, a magnified view of this nanoparticle shows that here the donor phase and the acceptor phase now stays in the same matrix. But here you see that donor phase is different, acceptor phase is different. We have attached them by physical interaction, by electrostatic interaction, but here both the donor and acceptor phase, they stays together inside this assembly, and that is called intradyad nanoparticle. So, this is basically a bulk heterojunction analog, and this is basically a layer by layer analog. So, now we wanted to see that whether this is better or whether this is better. Now our bulk polymer chemistry that teaches us that the bulk heterojunction solar cell is better than layer by layer, and what was the reason behind that? So if I take a donor and the acceptor, because of the small diffusion length of the donor of the charge carrier, so only those charge carrier which is at the interface, which is close proximity to the interface, they can contribute to the charge conduction. So to overcome that, we mix them together to make a phase separated bicontinuous percolated network. Similarly, if here like we electrostatically attach them together, the distance between the donor and the acceptor is higher than if we mix them together, where the probability of seeing the acceptor by the donor is much higher than the interdiode case. So the consequence is that not only the morphology by the self assembly, but the charge transport dynamics will be completely different in here than here. And by doing some sophisticated experiment, just like transient absorption, transient PL spectroscopy, we have found that, or by doing some like time correlated single photon countings experiment, TCSPC, which is basically nothing but a transient spectroscopy to look at the decay of the charge carrier, what we have found that two different kind of charge conduction mechanism works in these two different cases. In one of these cases, the electron transfer, in another case the energy transfer. One of the case you call it as a fluorescence resonance energy transfer or FRET, and another case you call as a Dexter electron transfer. In the case of the solar cell, like for a bulk polymer case, if you take a P3HT polymer and if you gradually add the acceptor molecule, you will see that the fluorescence from the P3HT polymer will be quenched. So that means there is an electron transfer from the LUMO of the P3HT to the LUMO of the PCBM. So similarly, the similar kind of phenomena has obtained in the case of intradiode nanoparticle. So here, because of the close proximity of the donor and acceptor, it is possible that the electron can transfer from the donor LUMO level to the acceptor LUMO level. But whereas in this case, which is physically attached with each other, there is not an electron transfer mechanism is possible, but an energy transfer mechanism is possible. So what it teaches us that this kind of system is more efficient for fabricating solar cell device than comparison to this kind of devices. So when we proceed to do some more advantage or more advanced characteristic or more advanced like experimental techniques to characterize this system, we found our this speculation or we are this observation. For example, here we are showing the differential scanning calorimetry or DSC data of this nanoparticle assembly, and this DSC data which actually plot the heat flow versus temperature, it shows that like different kind of packing or different kind of long range order exist in the intradiode system as well as in interdiode system. So in intradiode and interdiode system, two different kind of long range order and packing exist. So further optical characterizations like this for polymer and for the small molecule also prove us the same phenomena. Now whenever we do the fluorescence experiment with this nanoparticle system, we observe the similar phenomena like in the case of a bulk polymer counterpart in an intradiode case. So this is the fluorescence from the P3HT nanoparticle, okay, when we do not have any acceptor doping, but if we gradually increase the acceptor doping, nanoparticle fluorescence gradually decreased. So if I take the intensity decrease of the fluorescence, if I plot that on the y axis and if I plot on the x axis the acceptor concentration, we get the so called Stern-Volmer plot, and the slope of the Stern-Volmer plot is very high, which tells that these systems will be an efficient system for fabricating the device. Not only that, the energetics, the positions of the HOMO and LUMO energy level also matches in this nanoparticle assembly. You take a LUMO energy level of the P3HT, you take a HOMO energy level of the P3HT, you take a LUMO energy level of the NDI and take a HOMO energy level of the NDI. So basically their energetics is such that the electron can be injected from the LUMO of the P3HT to the LUMO of the NDI. So that means this system is also good for fabricating device. So guided by this idea, like what we have learned that this kind of nanoparticle assembly satisfies all the basic criterion for fabricating a device. The first criterion was that like to fabricate to maintain the energetics or the positions of the HOMO LUMO energy level, that is maintained in here. The second criterion was that in the presence of the acceptor the donor level fluorescence will be quenched, and that also we have observed there. If we gradually increase the concentration of the small molecule NDI, so we have observed the P3HT nanoparticle fluorescence is reduced. And not only that, what we also have observed that comparison between the interdiode and intradiode case, in the case of the intradiode where we have both the donor and the acceptor nanoparticle together in the same system, the charge carrier dynamics is completely different than in the interdiode case where we have a physical mixture. So, in the case of the intradiode we see a dexter electron transfer, whether in the case of the interdiode case we have seen that fluorescence resonance energy transfer. Now, we need a electron transfer for a sufficient donor acceptor pair or for an effective donor acceptor pair to have exist for making in a optoelectronics devices. So, that kind of criteria is also satisfied in this geometry. So, that is why this kind of systems will be very useful for fabricating organic nanoparticle solar cell, where you can circumvent the fundamental problem of the exciton diffusion length in a bulk polymer system. So, you see that even by the discovery of the best low band gap polymer, the efficiency of an organic polymer solar cell is limited to 8 to 10%. But this kind of approach can easily increase the efficiency of solar cell beyond 15%. And now there are a lot of research is ongoing where people have been trying to use the low band gap polymer for fabricating this nanoparticle, and different kind of like geometry, different kind of self assembly they are taking out for fabricating the devices. And by this continuous process we are hopeful that very soon the efficiency of this organic nanoparticle solar cell will reach to the efficiency of a silicon solar cell. So, in today's class we have learned that what are the different methods or the procedures of fabricating the organic nanoparticles, how to characterize the organic nanoparticles by different experimental methods, and while to fabricate a device what are the characteristics of the organic nanoparticle we should keep in mind, and how a particular class of organic nanoparticle assembly is advantageous to use over the other. And we have also seen that this kind of nanoparticle assembly satisfies all the criteria for fabricating an efficient solar cell device, and we are hopeful that this kind of organic nanoparticle device very soon will able to beat the efficiency of a silicon solar cell. Thank you so much.